Okay, have any of you heard of the Fibonacci numbers before? Kind of, yeah? So let's prove something about the Fibonacci numbers. Oh dear, how do I spell this? Two N's? I don't know. Okay, Fibonacci numbers. So the definition of the Fibonacci numbers is, let's say f1 is 1, f2 is 1, and then fn is equal to fn minus 1 plus fn minus 2 for n at least 2. Okay. Or in other words, right, I mean, probably the way you think of these things is, you start with the numbers 1 and 1, right? And then each term is the sum of the previous two numbers. So 2 is 1 plus 1. The next one is 3 because it's 2 plus 1. 3 plus 2 is 5. 5 plus 3 is 8. 13, and so on. So to get the next number in the sequence, you add up the two previous numbers. Right? Let's do a few more. So you got 21, you got 34, right? 55, okay, and so on. If you look at this sequence, actually you might notice, well, there's probably lots of different patterns in this sequence. One pattern kind of emerges if you think about where are the even numbers, right? So there's an even number. There's an even number. 34 is even. If we keep going a little bit, we get like 89, and then we get, oh dear, 144, and we see an even number there. So it seems to be, from the little bit of evidence that we have, that maybe like every third Fibonacci number is even, So the third one, the sixth one, the ninth one, 12th, and so on. So let's prove that. So every third Fibonacci number is even. Or in other words, specifically what I mean is for all n, f3n is even. So for all n at least 1, right? Okay. So I want to do this by induction on n. So what's the first step of induction? Yeah.
You gotta write a basis.
Exactly. Yeah. And so what should be my basis this time? So one thing, it's not entirely obvious what the basis should be. So, okay, there is one part of it that's obvious, which is the basis should include the case n equals 1, right? The basis is always like the first case or possibly the first few cases of the statement. Now, in this case, yeah, it's maybe hard to tell right away how many cases you need. All we're going to need is one, though. So the base case is going to be the case n equals 1. So consider n equals 1. And in this case, so f of f3 is just f2 plus f1, which is just 1 plus 1, which is 2. So why am I looking at f3? Because this is f sub 3 times 1, right? So my statement is that f3n is even for all n. So yeah, my first one is f3. And that's even. Okay, so that finishes the base case, the basis. Okay. So usually the basis is really that easy. You just plug in n equals 1 and show that the thing is true. Oh, okay. This was not drawn by me. Okay. What's the next step of induction after the basis? Anyone? Exactly. Yeah. So the next thing is always to state your inductive hypothesis. Okay. So I'm just going to use weak induction here because we don't really need strong induction. So the inductive hypothesis says, okay, take some number n and suppose, like it's kind of an assumption. We kind of assume we've proven it for one, or well, we assume we've proven it for the nth case, like for some n. And then we want to derive it for n plus 1. So let n be at least 1 and assume that f3n is even. Okay. You always want your inductive hypothesis to start at the last basis case you proved. The only basis case we proved was n equals 1. So this lower bound on n, this n at least 1, this should match. The 1 here should match the last basis case you proved, which was 1. Right? Because we're assuming it's true at n. If I started at n equals 2, we can't assume that's true because we haven't proven it. So you have to start at the first case you can assume is true, and then you have to build the next case. Okay. So inductive step. So without saying what the actual proof of the inductive step is, does anyone know what we want to prove for the inductive step? Yeah, exactly. Yeah. So we're assuming it's true for some value of n, and then you want to show that the next statement is true. So our next statement would be, so we want to prove that f of 3 n plus 1 is even. Okay, basically just taking your n and substituting an n plus 1, right? So in other words, we're dealing with f3n plus 3 because, okay, multiply out the 3. So what can I say about this? When I say about this, I mean, what do I know about f of 3n plus 3? Doesn't seem like much, maybe. But we do know this fact that, basically, f of n, for most, except for n equals 1 and 2, f of n is f of n minus 1 plus f of n minus 2, right? Okay, this might look weird because this is an n, and that's like a 3n plus 3. So you might be thinking, this is not an n or something, right? But, really what the point is that what this is saying is every element of the sequence is the sum of the two previous elements. So my two previous elements here are f3n plus 2 plus f3n plus 1. Okay, we have to somewhat remember that this statement is only true for n at least 2. So you have to kind of think, is this valid? But this is valid because the number I've got down here is definitely at least 2. So it's actually at least, I think since n is at least 1, this is at least 6, which is bigger than 2. Okay. Because we're only allowed to apply this formula when the thing in the subscript here is at least 2, and it is. So this is okay to do. Not sure if that's clear or not. Whether it's clear why I'm doing that, but okay. Any idea what to actually do with this? This maybe is not clear. So here's the trick. I can also apply the same thing to this. So if I look at f of 3n plus 2, yeah, can anyone help me out? How can I rewrite f3n plus 2? Yeah, so I think maybe the last bit was slightly, yeah, so it's like, it's the two previous terms. So f3n plus 1 plus f3n. But yeah, I think you had the right idea here. So, right, because every term of the sequence is equal to the sum of the two previous terms. So f3n plus 2 should be 3n plus 1 plus 3n. And then I've still got this f3n plus 1. You can see that you've got some repeated stuff here, right? So I can collect the terms. Okay, and we get that. Can anyone see why I'm in good shape right now? Why, when I say good shape, I mean this is going to work. I'm going to be able to prove what I wanted from here. Yeah, exactly. So we know that by the inductive hypothesis, this one is even, and then we're adding 2 times a number to it. If you add 2 times any number is even. So I'm taking an even number plus an even number, so it's an even number. So this is even because f3n is even. And this is where I'm using my inductive hypothesis. Okay, it's important if you're ever doing a proof by induction, at some point you have to use the inductive hypothesis, or else it's not induction. And 2 times 3n or f of 3n plus 1 is even. So that does complete the inductive step. And then I guess here's how I'll write my conclusion. A very lazy way, but conclusion, therefore every third Fibonacci number is even. So maybe I'll put a therefore before this by induction. Okay. So just imagine I rewrote that again at the end of the proof. Any questions about this? Okay.
How do you know to use the weak form?
That's a good question. Yeah. So in this case, you sort of can't necessarily know that until you've done the proof in some sense. So therefore, you might want to sometimes, to be safe, just do the strong form, because you can always, the strong form is always going to, if the weak form is going to work, then the strong form will also work. But here, the reason the weak form of induction worked is because to do the n plus 1 case, we only needed the case of n. We didn't need the previous cases that came before that. So that kind of tells you when the weak one is good enough, because yeah, if to do the n plus 1 case, all you need is the nth case, then weak is good enough. But like I said, before we started this proof, we didn't really know that was going to work, perhaps. So if I wanted to do, let's actually talk about, like, what would I change if I was using the strong form of induction? So suppose we use strong induction for this proof. Now let's just talk about, like, what would change. Like, what would we do differently? Like, the whole proof is almost exactly the same, but there's actually just one spot we would change what we wrote. I don't know if this question is even clear what I mean or not, but does anyone know what we would change? Sometimes when you do strong induction, sometimes the base case will change. Actually, you could, if you wanted to change the base case to do, like, okay, f of 3 is even, f of 6 is even, f of 9 is even. You could do a whole bunch of cases. That wouldn't have to change, though. You could still get away with the same basis for this one. So the main thing that changes when you change from weak induction to strong induction, the biggest change that always happens is the inductive hypothesis changes. Okay, so in a strong induction proof, the induction hypothesis looks different. So here we said the induction hypothesis was we let n be at least 1, and we assume that this particular value is even. We just assume, we make an assumption about one value. If we were doing strong induction, we would say let n be at least 1 and assume that f3k is even for all k between 1 and n. This is the main change that you would have in strong induction. Okay. So strong induction says we assume all the previous cases, and then we prove the next case. Weak induction says we just assume one previous case and prove the next case. But you can see, like, we can assume this, but we never use this in the inductive step, right? We didn't use all the previous cases, we just used one previous case. So, okay. Any questions about that? But it's always okay to use strong induction. If you want to get comfortable with just one type of induction, then get comfortable with strong induction because, yeah, it's a bit safer. Okay. So let's more generally talk about recursion. So, so this definition of the Fibonacci numbers, so this is something we can call a recursive definition. What do I mean by a recursive definition? So you're kind of building up a sequence, Fn, where each term of the sequence is built up from the previous terms. So it's kind of like I don't know if there's computer scientists in here, but it's kind of like a sort of loop or something like that. I mean, or, each term is built up from the previous two terms. So here what we did was I gave you a recursive definition, and we wanted to prove something about the sequence. A type of question that could come up, I'm not sure if it's going to come up or not, but is to kind of do something backwards. So suppose I give you some sequence or something, and I ask you to come up with a recursive definition. So suppose I say, let an be 2 to the n for all n at least 0. So the question could say, provide a recursive definition of an. So it's kind of a backwards question, right? So I'm going to give you the formula and ask you, please tell me how to recursively define this sequence. Meaning a kind of thing like this, where each term depends on some previous terms. Does anyone have an idea how to do it? Yeah? Yeah. Basically, yeah. There is always one thing that you have to also define. You can't just define this forever and that everything is 2 times the one before, because there has to be a starting point as well. But apart from that, that's exactly right. So, so if I let a0 be 1, because, okay, if I plug in 0 here, it does give me 1. 2 to the 0 is 1, right? And then you can say an is 2 times an minus 1 for all n at least 1. Okay, so that would be your final answer. And you can see that this is going to generate the powers of 2, right? a0 is 1, which is correct. 2 to the 0 is 1, so anything to the 0 is 1, right? Not 0. a1 is going to be 2 times a0, which is 2. a2 is 2 times a1, which is 2 times 2 is 4, and so on and so forth. So this kind of gives you like a machine for generating the terms based on the previous terms, or elements of the sequence based on the previous elements. What if I said, like, if I asked you to give me a recursive definition of n factorial, I want to put a question mark at the end of this, but it'll look like I'm like, you know, asking a question really like, you know, exclamation question mark. It's like I'm confused or something, right? But anyway. So how would I give a recursive definition of this? So I haven't actually, so here I wrote an is something, but I guess you have to come up with, I mean, a letter to call it. But so how do you kind of recursively define the factorials? Yeah. Exactly, yeah. So if we remember, I guess, yeah, I'm assuming people remember what the factorials are, but if you don't, then, you know, it's what you get by multiplying all the numbers all the way down, except for the 0 case. So 0 factorial, so this is something to remember, that 0 factorial is 1 as well, okay? So yes, that's the main part, is that n factorial is n times the previous factorial. So it's n times n minus 1 factorial. But there's another part you shouldn't forget. This starting case, this kind of basis thing. Always remember this. So here we could say a0 is 1. Like we're trying to come up with, in the end, that an is n factorial. That's kind of what we're trying to come up with. So 0 factorial is 1 by definition, and an is n times an minus 1 for n at least 1. Okay. And then it will be the case that an is n factorial. So this is a recursive definition of the factorials. Okay. Any questions about that? Let me also tell you something which is, I mean, slightly weirder than this, but okay, so we've been recursively defining sequences. You can also recursively define other mathematical objects. So so you can also, for example, recursively define a set, for example. So I know everyone was probably focused on the test last time when I gave the lecture before the test, but you might remember, I think, well, at least I think this is what we did. We did this thing about writing numbers as a sum of 3s and 5s, I think. So you could be asked, like, recursively define the set of all all non-negative integers that can be written as a sum of 3s and 5s. Okay, so this is a little bit different than recursively defining a sequence, but it follows the same principle, right? So in these recursive definitions, we had like a first case that we had to write down, and then we had like kind of the general case. So the first case I want to write down is that, well, so let X be a set, or let X be a set such that, so I'm going to say 0 is in X. Why is 0 in X? Well, if you think about it, technically, you can kind of think of like 0 you can write as a sum of 3s and 5s. You just don't use any 3s and you don't use any 5s. So 0 is in the set we want to define. And then the recursive part is that if, let's say, A is in X, then a plus 3 is in X, and a plus 5 is in X. Okay. And this is going to generate all the numbers that can be written as sums of 3s and 5s, right? Because you've got the first case, which is 0, and then you have 0 plus 3 and 0 plus 5. You then have 3 plus 3 and 3 plus 5 and 5 plus 3 and 5 plus 5, and all the kind of different combinations of 3s and 5s will end up being in X. So X will, if you kind of generate it recursively in this way, it will contain all the numbers that can be written as sums of 3s and 5s. Okay, this is kind of a weird one, but yeah. Any questions about this? Okay. Let me give you let's just keep on doing more examples of induction. So we'll kind of go back now to another inductive proof. So here's a nice statement. So if I take the numbers 1 plus, so suppose I take the odd numbers, okay, and I keep adding them up. So I take 1, 3, 5, 7, 9, etc., all the way up to 2 times n minus 1. So I claim that that is equal to n squared for all n at least 1. Okay. Let's check a few values just to, like, I don't know, play with this. So for the case n equals 1, right, we're summing up 1 plus blah, 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 up to 2 times 1 minus 1, which is 1. So my left-hand side is 1. My right-hand side is 1 squared, which is 1. Actually, this is going to be our base case, I guess, already, right? Or our basis. Is it clear how I got these numbers? I think the weirder one is trying to compute the left-hand side, because it looks like I need to, like, you have to realize that you're only summing the number 1 here, because it's everything between 1, all the odd numbers between 1 and 1, so it's just 1. I don't know. For n equals 2, on the left-hand side we get 1 plus 3. The right-hand side, which is 4, we get 2 squared, which is 4. By the way, let me tell you a common mistake, okay? If I was doing the case n equals 2, this is what a lot of people write. They start by writing, okay, what is my equation? They write 1 plus 3 equals 2 squared. Then they say 4 equals 4. Maybe they subtract and they say 0 is equal to 0. And they say, oh, I've proved it. But nobody told you to prove 0 equals 0. You see what I'm trying to say? Like, this is backwards. You can't conclude your proof by saying 0 equals 0. That's, now I'm happy, because nobody told you to prove that. What was asked was to prove that the left-hand side of this equality is equal to the right-hand side. What I've done here is backwards. I started by assuming, I wrote down the left-hand side equals the right-hand side, and I derived something which was, it's true, but it's kind of pointless. So this is a better way to do it. Write out what your left-hand side is, write out what your right-hand side is, and then say, oh, left-hand side equals right-hand side, so it's proved, you know. I'm not sure if the difference here makes sense, but there is a subtle difference. So what I'm trying to say here is don't do this. Don't start out by writing what you're trying to prove and then simplifying both sides, because you'll end up proving 0 equals 0, but we kind of know 0 equals 0. It's not really, yeah, that's not the point. Is it clear what I'm saying there? So a better way to do is compute the left side, compute the right side, show that they're equal, and that proves it. Okay, let's do this by induction now. So okay. So my basis, I've kind of already done it. So for n equals 1, the left-hand side is 1, right-hand side is 1. So left-hand side equals right-hand side, and we're happy. So what's my inductive hypothesis? And it's going to turn out, again, we only need the weak one, but we can do whichever one you want. So, so maybe I'll give you guys this one. So let n be at least 1, and assume that 1 plus 3 plus 5 plus dot 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 up to 2n minus 1 is equal to n squared. So we're assuming it for the nth case. And now what do I want to prove for the inductive step? So we want to prove well, we want to prove the next case. So we want to prove this statement except where all the n's are actually n plus 1s. So we want to prove that the sum 1 plus 3 plus blah, 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 up to, so maybe I'll write 2 final terms here. So if I add up the first n plus 1 odd integers, I want to show that that equals n plus 1 squared. Now, similar to this base case, what you should not do is you should not write this down and then try to simplify both sides and end up with something like 0 equals 0, or n equals n, or n plus 1 equals n plus 1. Because we're not trying to prove 0 equals 0. We're trying to prove that this equals that. So your conclusion shouldn't be something like 0 equals 0. Your conclusion should be that this equals that, right? So the best thing to do here is just start by writing the left side and don't write the right side. Start by writing the left side, break it down until you get it that it's equal to the right side, and then you've proved it. So my left-hand side is 1 plus 3 plus 5 dot 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 up to 2n minus 1 plus 2 n plus 1 minus 1. Okay. Any suggestions for what to do with this? Yeah? Yeah. You want to take this thing and simplify it using the inductive hypothesis, right? Exactly. Yeah. Perfect. So this is the thing to notice. If I take all of this sum except for the last term, I know what that is. I've got a formula right here for it. So yeah, let's substitute that in. So this is equal to n squared plus this last thing, which, by the way, is equal to 2 times n plus 2 minus 1, so plus 1. So by the inductive hypothesis, right? So I'm just using this equation. And now you factor it, right? N squared plus 2n plus 1 is equal to n plus 1 squared by algebra, which is equal to the right-hand side. Okay. So that's it. That's the proof. So conclusion. So therefore, 1 plus 3 plus dot 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 up to 2n minus 1 equals n squared for all n at least 1 by induction. Okay. And just algebra, right? So if you were to multiply this out, you'll get this, like n squared plus 2n plus 1. It's just factoring a quadratic, basically, right? Find two numbers that add to 2 and multiply to 1. It's 1 and 1, so it's like that. If you got really stuck at some point with some thing and you don't know what to do with it, like you can use all the things you learned, like what do you call it, quadratic formula or whatever. You know, you can, but yeah, it's just solving a quadratic or whatever. Okay, so I think until you get some actual practice doing this, you might find these steps kind of mysterious. So let's get a little bit of practice doing this. So I'll give you an ICA now. And then we'll come back to the lecture after that. So I'll give you maybe 5-10 minutes. Ooh. Okay. Okay, so the point is to prove, so we've got the sequence A1 is 2, for n at least 2, an is 5n an minus 1 plus 12, so it's like this, a recursive definition, and I want you to prove that an is equal to 5 to the n minus 3 for all n at least 1. Okay, and I've broken the question down into steps, so which are the usual steps in induction. So you've got your basis, so submit that, your basis separately to question 1, inductive hypothesis, inductive step, and conclusion. Okay, so feel free to chat, ask me questions and whatnot. And I'll pause the recording. So let's, let me tell you about, well, okay, so here I've just written down some mathematical facts. So the first one we actually proved already. So I think this was like our first example of induction. If you add up the numbers from 1 to n, you get n times n plus 1 over 2. These ones are all very similar. So these are, you know, not hard to prove. By induction. Okay. So if you sum up all the squares of the numbers up to n, you get this. I mean, none of these are very enlightening, I guess. So this one, the fourth one is kind of different. So it says if I take a number, a real number x, which is not equal to 1, and I add up 1 plus x squared all the way up to xn, x to the n, I get x to the n plus 1 minus 1 over x minus 1. For now, let's just kind of treat these things as things that we just memorize. But it's, like I said, you know, if you can easily prove these by induction. The proof is very much the same as what we gave for this one, or what we just did for like the sum of the odd numbers. It's the same proof, basically. By the way, can anyone tell me, or can anyone see why I'm picking x to be a real number that's not 1 here? Like, what would go wrong if I picked 1? Yeah. If I put x equals 1, I'm dividing by 0, right? So that doesn't make sense, right? Because this would be 0 over 0, and you know, you can't divide by 0. So that's the only reason that x is not 1. Okay. What I wanted to give you now is an example of, suppose I give you a recursive definition. For example, like the one in the ICA, you know, suppose I tell you. So this will be a different recursive definition, but so suppose that, you know, I give you that a0 is 4, and an is 3 times an minus 1 plus 5 for n at least 1. And suppose, like, so as you saw in the ICA, what the way it was structured was I gave you a formula for an, and I asked you to prove it. But you could imagine a question where somebody asks, well, please find the formula for an and then prove it. So how do we find the formula? The formula for an. That's what we're going to talk about next. Okay, and some of these special sums will be kind of useful for that. That's why I give them to you here. Now, I have to say there's not just one answer to this. Like, this is it's a general question. How do you find solutions to these kind of recursively defined sequences, it's a pretty deep question, but we're only going to look at one sort of method. So the method we're going to kind of come up with here is a sort of guess and check method. Okay, but it's not going to be a complete guess. It's going to be an educated guess, okay? We're not just going to randomly guess something. Okay. So here's a way you can start to guess a solution. So suppose I'm just going to write A0, okay? So A0 is 4. So I'm going to start writing out terms of the sequence, but I'm not going to completely compute them, because maybe I'll kind of demonstrate in a second why that would be a bad idea. But if I actually compute A1 exactly and compute A2, A3, A4, etc., it's not going to be clear what the pattern is. The better thing to do is kind of leave it as a sort of algebraic expression. I know that's extremely vague, so let me demonstrate. So A1 is 3 times A0 plus 4, which is, or sorry, plus 5, which is 3 times 4 plus 5, right? But so I could write 17 here, but the 17 isn't going to help me very much. So I'm going to leave it like this. And then I'll write A2, which is 3 times A1 plus 5, okay, by definition. So that's how these recursive definitions work, right? Now I'm going to plug in this thing I got for A1. So it's 3 times 4 plus 5, and then plus 5. So it's 3 squared times 4 plus 3 times 5 plus 5. Okay. Which again is weird, because why wouldn't I just compute this? But the point is that we're going to start to see a pattern that forms. And if I compute these actual numbers, you won't be able to see the pattern. So A3, so we take 3 times A2 plus 5, which is going to be 3 times 3 squared times 4 plus 3 times 5 plus 5, and then plus 5 at the end. So it's 3 cubed times 4 plus, so this is not 35, this is 3 times 5. 3 squared times 5 plus 3 times 5 plus 5. Okay. Can anyone already see a pattern? Should I do another one before we see the pattern? Yeah.
AN is 3 to the n is 5, 2 to the n 5, plus 1 to the n minus 2.
Yeah, and kind of all the way down kind of thing, right? Exactly, yeah. So it's, yeah, exactly. So we can see that, like, we're building up powers of 3 and then times 4. And then you've got, like, yeah, 3 to the n minus 1, 3 to the n minus 2, dot, 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 all the way down to 3 to the 0 times 5. But right now, that's not a proof, right? This is just a guess. But it's a kind of educated guess that maybe AN is 3 to the n times 4 plus 3 to the n minus 1 times 5. So sorry, this is a little bit small, but 3 to the n minus 2 times 5 plus dot, 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 all the way down to 3 times 5, which is 3 to the 1 times 5, plus 3 to the 0 times 5, which is just 1 times 5. So this is like, sorry. We can actually kind of simplify this a bit. So what I'm going to do is simplify our guess and then prove that it's true. So maybe let me rewrite this, because that was kind of not great. So 3 to the n times 4 plus 3 to the n minus 1 times 5 plus 3 to the n minus 2 times 5 plus dot 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 down to, like, let's say it's 3 squared times 5, 3 to the 1 times 5, 3 to the 0 times 5. So yeah, like I said, let's try to simplify this a bit. So I can't do much about the first term, 3 to the n times 4. But this one I can factor out a 5 from everything, right? Okay, it's not much simpler. It's kind of the same, equally as complicated as what we had before. But how would I simplify this now? A little bit. Ah, I see what you mean. So no, it's not. It doesn't quite work like that. If I add up these things, it doesn't multiply the exponents. If I actually, yeah, you'd have to, like, take exponents to the exponents, then you multiply exponents. So actually, the trick is kind of here. Although it looks kind of backwards and a little bit different, but this is like, so if I take, this is kind of like this sum where x is equal to 3, except it stops at n minus 1 instead of n. But, so applying the, well, so this is called a geometric series. So if you take 1 plus x squared all the way up to x to the n, that's called a geometric series. Let's say, so applying the geometric series formula, let's say. I'm not sure if this is the official name or not, but this gives us 3 to the n times 4 plus 5 times. So does anyone know what it is? So I kind of want to apply this with x equals 3, but we stop at the n minus 1 term instead of n. So well, it's just going to be 3 to the n minus 1 over 3 minus 1. So I plug in x equals 3. It pretty much looks the same, except that, yeah, I stop at the previous, but then I sort of plug in n minus 1 in for n in some sense. And I get 3 to the n minus 1 over 3 minus 1. Which we can simplify further. So the denominator here is 2. So let's get everything under the same denominator. So it's 3 to the n times 8 over 2 plus 5 times 3 to the n and minus 5 over 2. So here I'm just putting this under the same denominator, multiplying that through, which is 13 times 3 to the n minus 5 over 2. So if anyone was able to just guess this by looking at the definition, then, well, kudos to you. But that's the sort of thing I wouldn't be able to just guess. But you can sort of, yeah, you can make an educated guess by building things up like this, by writing out a few terms without simplifying and then making this kind of educated guess. By the way, if I did simplify this, they'd be horrible. So it turns out, like, if you compute a few values of n, so for n equals 0, I get 4, because that's the definition. For n equals 1, I get 17. For n equals 2, I get 56. For n equals 3, I get 173. Then 524. Then 1577. So if somebody gave you those numbers and said, spot the pattern, well, good luck. I mean, maybe you can do it. I can't do it. But the thing is, when we multiply them out and we don't simplify, we keep them in this form at the end, you can kind of see the pattern. So yeah, so I guess don't compute the final numbers because it's not useful. Yeah, so if anyone can see that like these numbers are the same as like these numbers for each n, that's, yeah, that's kind of amazing. Okay, any questions about any of this? Okay, so then let's prove that this is true. So again, maybe I'll repeat the sequence. So A0 is 4, and AN is equal to 3 times AN minus 1 plus 5 for n at least 1. And we want to prove that AN is 13 times 3 to the n minus 5 over 2 for all n at least 0. Okay. Okay. Okay, what's my basis? Now you might see these two things here. You might see this n at least 1, and you might see this n at least 0, and be wondering, like, which one of these is the basis? I can't tell the difference. It's this one, right? It's the n at least 0 is the key thing, because this is what you're asked to prove. So this part of the question is just a definition. This is just telling you what the sequence is. This is the part where I'm asking you to prove something. So if I'm asking you to prove something for all n at least 0, your basis case is n equals 0. So for n equals 0, the left-hand side, when I say left-hand side, I mean of this equation here, right? This is the equation I'm trying to prove. The left-hand side of the equation is A0, which is 4, just by definition. Right-hand side, well, right-hand side is what you get by plugging in 0, which looks like it's going to be nasty, but it's not. Right? It's 13 times 1 minus 5, which is 8, over 2, which is 4. So this is our basis. Okay. Inductive hypothesis is, so let n be at least, well, 0, because that's our last basis case, and assume that AN is equal to 13, 3 to the n minus 5 over 2. So what should I do for my inductive step? So we want to prove something. So maybe we're kind of running out of time, so I'll just kind of write it. But we want to prove the next case, which is that AN plus 1 is 13 times 3 to the n plus 1 minus 5 over 2. And again, what I shouldn't do is just write this down and then simplify both sides. You know, start with one side. And the side to start with is probably this one. So my left-hand side is AN plus 1. Okay. What should I do with this? Yeah. Oh, plug in, right? Exactly. I'm going to use my recursive definition. Every term of the sequence is equal to 3 times the previous term plus 5. except for a0, because there's no previous term, right? But in particular, an plus 1 is going to be 3 times the previous value plus 5. Now, by my inductive hypothesis, I know exactly what an is. It's just, an is just this. So let's put that in. So an is 13 times 3 to the n minus 5 over 2. And now it's just algebra. So I've got 13 times 3 to the n plus 1 minus 15 over 2. I'm going to put this over 2 as well. Plus. So this is 10 over 2, which is 5 is 10 over 2. I combine this. I get 13 times 3 to the n plus 1 minus 5 over 2, which is equal to the right-hand side. So we're happy. So conclusion is that an is 13 times 3 to the n minus 5 over 2 for all n at least 0. Okay. So this was a more complicated example. We had to figure out the formula and then prove it. But yeah, hopefully the steps were somewhat clear. All right, so let's do, I'm going to do one more induction example, and then we'll move on to the next chapter. So claim, so for x, a real number other than 1, and any natural number, the sum 1 plus x squared plus dot 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 up to x to the n is equal to x to the n plus 1 minus 1 over x minus 1. Okay. Okay. So I want to do this by induction on n. So maybe I'll do this one kind of quickly. We've seen a lot of examples by now. So proof, I'm going to do my basis. So by the way, before I start that, I've kind of got two parameters here, right? I've got x and I have n, right? But hopefully it's clear, I'm not going to do induction on x because that's not going to make any sense, right? X is a real number. You can't really do induction on the real numbers. So we're going to be doing induction on n. Oh, and by the way, another thing here is why do I care? I think I mentioned this last time, but when I wrote this sum down last time, or this expression, but why do I omit 1? The reason is because I don't want to divide by 0, right? Division by 0 is not allowed, so that's why you have to omit 1. Okay, so basis is, consider the case n equals 1. Left-hand side is the sum 1 plus x dot 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 up to x to the 1, which is just 1 plus x. Right-hand side. So this time, it's not going to be immediately clear why the right-hand side is equal to the left-hand side, right? So the right-hand side, if n is 1, I get x squared minus 1 over x minus 1. But can anyone see why this is good? Yeah. Exactly. Yep. So difference of squares. So you got to remember all these tricks you learned in high school, and then you can cancel, and that's equal to x plus 1. Well, 1 plus x is the same as x plus 1, so therefore it's true for n equals 1. My induction hypothesis now is let n be at least 1 and assume that I assume that the statement holds for x, or sorry, for n. Okay. So again, we're going to use weak induction because I don't really need the strong version. So in the inductive step, we want to show, well, so we're assuming it for the nth case, and we want to show it for the n plus 1th case. So we want to show the same statement, but with n plus 1 substituted in for n. So I'm not sure, is it clear why this is the statement we want to show? Okay. Hopefully we're getting used to these proofs by now. Okay, how am I going to do this? Any thoughts? Yeah, that's a good place to start. Yeah. So let's write it out again. Maybe I'll write it out like this. I'll go to x to the n and then add on x to the n plus 1. And what am I going to do with this? Yeah, exactly. And that's, I mean, really, once you've done enough of these things, this is the way that these proofs work, right? You know, you got your statement with your left-hand side with the n plus 1 case, and you can just see the nth case is just sitting right there, right? So this thing we just know is equal to this. So we can say that this is equal to x to the n plus 1 minus 1 over x minus 1 plus x to the n plus 1, and we write by inductive hypothesis. Don't forget to write this. So some people lost some marks on the ICA because, you know, you have to give some reason for things, right? And yeah, so it has to be clear, when am I using the inductive hypothesis? Okay. Now it's just algebra, and that's kind of also how these things are going to usually go. So I want to get these things, I want to add these up. Got to get them under the same, or over the same denominator, right? So I've got x to the n plus 1 minus 1 over x minus 1. I want to get this up over the denominator x minus 1, so I kind of multiply top and bottom by x minus 1. Okay, and a magical thing happens. Where, so I get x to the n, well, maybe I'll write out the steps. So x to the n plus 1 minus 1 plus x to the n plus 2 minus x to the n plus 1. And magically, this cancels with that, right? And I'm left with exactly what I wanted. So which is equal to the right-hand side. Okay, so I've proven the left-hand side equals the right-hand side. Okay, so that actually does the inductive step. We now got the conclusion. So conclusion, I mean, I guess the whole point, the whole reason we make you write conclusions is so that you understand what you've actually proved. So yeah, so the conclusion is that for all x in the reals except for 1 and n at least 1, the sum 1 plus x plus dot 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 up to x to the n is equal to x to the n plus 1 minus 1 over x minus 1. Basically, always the conclusion, you're just going to rewrite what you were asked to prove at the beginning.